In this video, we'll derive some expressions for how properties of a gas change across an oblique shockwave. The overall approach to the analysis is similar to the approach that we used for analysing normal shockwaves. That is, we'll conserve mass, momentum, and energy. So here is our oblique shockwave. And here is the notation we developed in the last video where we formulated the problem. We'll start our analysis here with the momentum equation. With our oblique shockwaves, we've moved on to two-dimensional flow. So we'll be able to obtain forms of the momentum equations in more than one direction. So let's consider directions parallel and normal to the oblique shockwave. That is, we'll apply momentum conservation in what we've called the tangential and normal directions. Let's start with the tangential direction. So we're going to be looking at momentum conservation. And we're going to apply that in directions tangential and normal to the shockwave. So we'll start with the tangential direction. And we can say here that the sum of the components of force in the tangential direction is equal to the integral over a control surface encompassing our flow of rho v dot dA, so our mass flow rate, and the component of velocity in the direction tangential to the flow. Let's go back to our Schlieren image and let's put a couple of streamlines in. So there's a streamline upstream of the shockwave and then one parallel to the wedge downstream, and we'll put another streamline in down here, so upstream and parallel to the wedge downstream. Now, just as we did for normal shockwaves, we're going to consider a control volume just immediately upstream and downstream of the shockwave. So we're going to be let's put this little control volume around this section of the shockwave between those two streamlines that we've drawn. So that's our control volume, CV. And we'll just put our velocities coming into the control volume, the upstream velocity, and then exiting the control volume will be our downstream velocity. So that'll be V2 and V1. So that's the control volume that we're going to apply this conservation of momentum to. So we've said that the sum of the forces in the tangential direction is equal to this integral. Let's look at what those forces are and what that integral is. So the forces on the control volume in the tangential direction, well, there's no forces that are going to apply in the tangential direction at all. So that left-hand side is going to be 0. The right-hand side, we've got basically the mass flow rate times the change in the tangential component of velocity. So the mass flow rate entering the control volume is equal to the mass flow rate leaving the control volume. We'll get that out of the continuity equation, or the conservation of mass. So m dot is going to be the mass flow rate, and we just need to look at the change in the tangential component of the velocity across this control volume. And we have that in terms of our notation over here on the left-hand side. So coming out is going to be tangential component VT2, that one there, and coming in is tangential component VT1. So immediately coming out of this, we're going to get a relationship which is going to say that the velocity component tangential to the shockwave downstream minus the velocity tangential upstream must be 0. So therefore, there's no change in the tangential component across the shockwave. So VT2 is equal to VT1. So this is the first important result. Very important result. Put a nice little exclamation mark there. So there's no change in the tangential component of the velocity across an oblique shock wave. And this will be a very useful result for us. Let's move on now to our conservation of momentum, and we'll look at the normal component. And again, it'll be the change in the forces are going to equal the change in the momentum flux. So the forces upstream, we've got pressure forces acting on the control volume normal to the control volume. So we'll get out of this P1 minus P2, and we're going to get some change in the momentum, and this will come out to be ρ2, density of the flow coming out, Vn2, because we're interested in the normal components of velocity, squared, minus ρ1 Vn1 squared. And we've got rid of the a's there because they'll cancel out. We'll write our conservation of mass, or our continuity equation, for completeness. So the continuity equation will be what's coming in, ρ1 Vn1 times its area, and that will equal what's going out, ρ2 Vn2 times its area, and we've got rid of those areas again. And then we can also write down an energy equation. So we've got the flow coming in with some static enthalpy, let's say it's H1, and then it's got some kinetic energy, or specific kinetic energy, and it's got two components to that. So it's going to be a half Vn1 squared plus a half Vt1 squared. And that must equal what's coming out. So we've got some static enthalpy again, H2, and some specific kinetic energy, a half Vn2 squared plus a half Vt2 squared. And all of that is equal to the total enthalpy H0, which is unchanged across the shock wave. Now let's look at the Vt components. So we've got a half Vt1 squared on the left hand side and a half Vt2 squared on the right hand side, and we've said up here that Vt1 is equal to Vt2. So those two terms are equal, so they'll cancel out. And what we're left with is we get that H1 plus a half Vn1 squared is equal to H2 plus a half Vn2 squared. Now let me just slide that screen down a bit. Go. Now I want to bring up a result from our normal shock analysis. So we found from the analysis of the normal shock waves the following. We had a relationship for how the density times velocity changed across the normal shock wave. From our momentum equation, we had a relationship between the pressure and the change in ρv squared, and we also had our energy equation. Now, if you have a look at the equations we've just derived on the top of the page up here, you'll see that they're identical to the ones that we derived for the normal shock waves, except for one point, where we had V1 and V2 for the normal shock waves, we now have Vn1 and Vn2 for the oblique shock waves. That our equations are identical, but we have V replaced by Vn. So this is the important consequence of that. All the normal shock relations and the tables that we've already derived and developed for the normal shock waves can be used for oblique shock waves just by replacing M1 and M2 by the normal components of the Mach number. And let's note that Mn1, the component of Mach number upstream of the shock, normal to the shock, is going to be the Mach number times sine of beta, the shock wave angle. And Mn2 is equal to the Mach number downstream of the shock waves times sine of beta minus theta. And you can see that from looking at the geometry up in our sketch up here. So let me just slide the screen down again now, and I'll write down the important relationships. The first result we obtain is for the density ratio across the shock, the static density ratio, rho 2 over rho 1, coming out in terms of gamma and mn1. And from our continuity equation, we can directly relate the density ratio to the velocity ratio, and again, components of velocity normal to the shock wave. And from the geometry, we can relate the normal components to the tangential components through the angle of the shock wave and the angle of deflection, so beta and theta. But we've said that Vt1 is equal to Vt2, so we can cancel those from the top and bottom, and we end up just with tan beta over tan beta minus theta. And I'm going to call that equation star because I'm going to come back to that. And we can write down our relationship for the change in the static pressure across the shock wave and our temperature ratio across the shock wave, again in terms of mn1 and gamma. And we can also write down an expression for the component of Mach number normal to the shock wave downstream of the shock. The last thing I want to do here is I want to look back at equation star. We've got the tan beta over tan beta minus theta, and we've got a relationship between mn1 gamma. Let's put that together. So let's say from equation star, we can get a relationship between our flow deflection angle theta, our shock wave angle beta, and our upstream Mach number m1. And this is it. So we've got tan beta over tan beta minus theta is this function of gamma, the Mach number upstream m1, and the shock wave angle beta in there. So in order to get that, we've just said that mn1 is equal to m1 sine beta. And this is a really useful relationship because it shows us the relationship between the Mach number, the flow deflection angle, and the shock wave angle. And we'll find that that will be a very useful thing for us to use. Let's just have a quick review of what we've developed here. We have expressions for the change in static pressure, static temperature, and static density across an oblique shock wave. Just as for the normal shock wave, we found that these ratios depend only on the ratio of specific heats, gamma, and the Mach number upstream of the shock wave. In this case, the component of Mach number normal to the shock. We also have an expression for the component of Mach number downstream of the shock wave, mn2, and we can use that with the shock angle beta to find the value of m2. Finally, at this point, we have a relationship between theta, beta, and m1, the flow deflection angle, the shock angle, and the upstream Mach number. It's this final relationship that will be the focus of the next video.